Alright, so before we get into our algorithms too far into our optimization, I just wanted to remind us a little bit about linearization. We've already talked about this before, but I just wanted to touch on it again, just as a reminder, because people don't see it very much. Um, so, um, we'll remind ourselves what the Taylor series is. So f of x at a point A is represented by f of a plus f prime of a times x minus a plus f double prime of a over 2 factorial x minus a squared plus dot dot dot. And so you could approximate f of x really. You could say like a degree 0 approximation to f of x would be f of x is approximately equal to f of a. Next to a, that's a pretty good approximation. You could use a degree 1 approximation. And so that way you would add in your line here, right? But you could keep going, right? You could have a best fitting parabola for your f of x by just including the second order term. And so on. So yeah, we could approximate our function to any degree. Usually we stop at 1. And similarly, we can, if z is equal to f of x, y, so if we increase the dimension a bit, and we're analyzing it at a point A, B, then, oops, let's see if I can write this down. Okay, so we could, thought I'd get a head start here and write down a few terms. So I've got the linear part of my function, f of xy, can be approximated by the constant term f of ab plus f sub x at ab times x minus a plus f sub y at ab times y minus b. And then you could continue, right, with the second order terms. You could say f sub xx at ab times x minus a squared plus f sub xy at ab times x minus a times y minus b plus, oops, by the way, those are divided by 2, f sub yx and so, by the way, these are telling you what your terms are here. So if I've got a y and an x there, I've got my y and my x over here. And notice, by the way, that as you start getting higher and higher in dimension, you start getting terms that are actually equal to each other. And so you could combine those into one. I'll just go ahead and finish that up here. And then you could go even higher, right? You could say third derivative at ab times x minus a cubed plus dot dot dot. Okay, so you kind of, I hope you see the idea there, because we don't usually do the multivariate Taylor series, but it's kind of fun to look at. Okay, so more specifically, I should say, we would just stop at the tangent plane, which would be just this, right? Change this to an approximate, and then we would just have the tangent plane. Good, all right. Now, when we take a function of more than one variable, so if we have like y, whoops, good, so if we have y equals f of several variables, right, then the derivative is replaced by the gradient, right? And so the gradient of f would be partial f partial x1, partial f partial x2, partial f partial xn. I'm having my Calc 3 flashback and using brackets But you can think of this as a row vector, or actually a column vector. I mean, it's not going to matter as long as you're consistent in your linear algebra. So I'll go ahead and use the angle brackets like calc for now. I don't know if I did that in the notes or not. Probably not. I think I just used square brackets. Oh well. Okay, whatever. So then, what takes the place of the second derivative? The second derivative is called the Hessian. The Hessian of f is a matrix of second derivatives. So I'm going to use the subscript notation. So that's partial f. And then it's j first, then I. So partial xj, partial xi. Whoops. Okay, so then like this would be f11, f12, f13, f1n, right? If we have n variables. And then f21, f22. So this is the matrix of all second partial derivatives. Okay, and so that matrix is how big? This is n by n, right? I'm going to denote this, by the way, as hf. And it'll always say somewhere, this is the Hessian. Okay. And you might note something about this matrix that, did you spot it? It is symmetric. So this is symmetric. And we know the importance of symmetric matrices, right? Symmetric matrices satisfy the spectral theorem. And so nice things happen with eigenvectors. Okay, but that's for another spot here. All right, so what is the linearization then of our multivariate function? So the linearization looks like f of x, that's the x is now in Rn, right? Is approximately equal to f of a plus the gradient of f at a times the vector x minus the vector a, right? Then you can also take on this next term, and the way you would write it, the quadratic term, is you would write 1/2 x minus a transpose times our Hessian matrix evaluated at the vector a times x minus a. And so just to emphasize this, right, this is 1 by n right here. This is n by n, right? And this is n by 1. So altogether then you have an 1 by 1. So that is a scalar. Okay. Good. So let's do a quick example. And we will we'll build our quadratic approximation to the function f of xy equals x sine y plus y squared plus xyz plus z at the point 1, 0, 2. Okay, so let's compute everything that we need here. So that basically says to compute all the first derivatives and all the second derivatives, right? So f of 1, oops, sorry, that's an xyz. F of 1, 0, 2 is equal to 1 times 0 plus 0 plus 0 plus 2. Good. So f sub 1 is the derivative with respect to x. So that's going to be sine y plus derivative with respect to x, so yz, evaluated at 1, 0, 2. And that's going to be sine of 0, 0. That's 0, so that's 0. F sub 2 is the derivative with respect to y, so x cosine y plus 2y plus xz. And again, that's evaluated at 1, 0, 2. And so f sub 2 is equal to 3, I think. You'll have to double check me on that. F sub 3 is the derivative with respect to z, which is xy plus 1, evaluated at 1, 0, 2, and that is 1. Good. And so therefore, the gradient of f at 1, 0, 2 is the vector 0, 3, 1. Good. All right. How about the second derivatives? So we have our f1, f2, and f3 there. Right, so what's f11? Looks like f11 is 0, right? What's f12? It'll be cosine y plus z. And f13 would just be your y, right? f2. f21 would be cosine of y plus z. Notice we're symmetric, right? And then derivative with respect to y would be minus x sine y plus 2z. These are in the notes as well if you want to just follow along and not write everything. And then finally the f23 would be the derivative with respect to z and I see I made an error somewhere that's supposed to be a z there. Did that change my derivatives everywhere? Let's see, this needs to be a z here. I think that's all that changed. We'll check as we go along. So this became a 2y plus x, and that's what got me started on that. So then I'll let you check on the third one too, because actually we don't have much to compute now, right, because of the symmetry. Then evaluate that at 1, 0, 2, and you get the matrix 0, 3, 0, 3, 4, 1, 0, 1, 0. Good. So therefore, our function is equal to 2 plus 0, 3, 1 times x minus 1, y minus 0, z minus 2 plus 1/2 times x minus 1, y minus 0, z minus 2, that's a vector there, times our 3 by 3 times our x minus 1, y minus 0, z minus 2. Good. And so that is our function up to second order. And so you could play around with that a little bit if you want. When we come back, we'll go through the last case, and that is a function from Rn to Rm.